Hello. In this video, I want to look at absolute and conditional convergence. So basically, we looked at the alternating series test, of which that we saw that there had to be like two conditions to be met. But one thing of which that we can talk about, for example, is absolute and conditional convergence. Now, for instance, let's say that you have a series such as like sine of n divided by, let's say, like n squared. And this is n equals 1 to infinity. Well, if I was to expand this, I would have sine of 1 divided by 1 plus sine of 2 divided by 2 squared. And we'll put it 1 squared, why not? Now, of course, notice that, the sine will have positive and negative terms because you learned that a sine function oscillates between a negative value and a positive value, in particular -1, 1, depending on the amplitude that is. But, we have that if in fact we were to, let's say for example, take the absolute value. Okay. If I take the absolute value though, the one thing that is interesting is that now you're no longer looking at the like the plus or minus terms, that is. So here's what we have. We have that the sine of n divided by n squared, well, we have that basically that this would have to be less than or equal to 1 over n squared. Now, of course we got that because sine of n will be less than or equal to 1 for all n. So, and this is valid for n is greater than or equal to 1, right? Okay. Now, what do we know about the series of 1 over n squared is that it converges by our p-series test. Okay, so we have that it converges by the p-series test, and notice that basically the inequality is in the right form that we want. So this would be a convergent series. So we have that the series of sine of n divided by n squared, it converges by the comparison test. Okay. Now, of course, if you wanted to, we could probably use perhaps like if we were going to look at the limit comparison test, but you probably would find that the limit comparison test is not actually going to be conclusive necessarily. So we would need to basically kind of use a comparison test. Now, what we can start with, because notice that, well, this one didn't alternate at all, and the other examples that we had, they all alternated. So what we'll say is that basically that we'll make a few statements. We'll say that if we have that the series of an with its magnitude, that if this converges, then basically we have that the series of an also converges. Okay. Now keep in mind that an is an alternating series. Okay. So with that, basically that all that we would need to show is convergence thereof. Now, we'll make some more examples, or like statements, if you will. So we'll say that the series of an converges absolutely if the series of an converges. Okay. Now, the other statement that we could make, for example, is that the series of an, it converges conditionally if, okay, this is where it gets a little weird. We'll just say not if, but when. Okay, so we'll say that when the series of an converges, but the absolute an, that it diverges. Okay, so what we're saying in here is that it's conditionally convergent when you have that the series under the absolute diverges, but then you have the series of the alternating, it converges. Okay, that's kind of interesting, actually. So let's say that you have an example, and if you have an example such as like -1 to the n, let's say like n plus 1, and this is divided by n squared, and this is from n equals 1 to infinity. Well, according to our statement, is that if we take the absolute, what is that? That's equal to the series summation n equals 1 to infinity of 1 over n squared. But basically, we could apply the p-series test, which says that p equals to 2, which is greater than 1, which naturally says that this is a convergent p-series. Now, because we're saying that under the absolute that it converges, this would imply that the series of -1 to the nth plus 1 over n squared, it converges absolutely. Now, I actually do have, I believe, a diagram or like a calculator demonstration where we look at, for example, the sequence of terms, -1 to the n plus 1 divided by n squared, and you see that here the values of the series summation is converging. It's alternating, but basically you have that it goes to 0.822, and that value is actually pi squared over 12. But look at the terms. Wow. Look at these terms. Like, they are oscillating between a positive and a negative, but they're always getting smaller and smaller. So to show that this series converges, you could show that this series converges by alternating series test. But here, all that we had to check was the absolute, of which once we looked at the absolute, it's a p-series, which p is equal to 2, greater than 1, so it's convergent. Then in that case, automatically by definition, you have that alternating series converges absolutely, and that's it. Well, only thing though is that, like, what if you were to switch the sign? Like, what if you had that it was n equals 1, and you have -1 to the nth plus 1, and this is divided by n, and that goes to infinity. Well, under the absolutes, you have that would be basically that you're looking at the series summation of 1 over n. But basically, you find that this is a divergent harmonic series. So you have that under the absolutes that it's a divergent harmonic series. But notice that now, like, if you were to say, like, okay, well, applying an alternating series test, well, an is 1 over n, which goes to 0. But an plus 1 is equal to 1 over n plus 1, which in any case, we have that 1 over n plus 1 is less than or equal to 1 over n, which is essentially the an, and this is the an plus 1, which means that basically you have the first condition, which says that they're decreasing, the second condition, which says that the an plus 1 term must be less than the anth term, which means that the series the series negative 1 to the nth plus 1 over n, it converges conditionally. And similarly, if we were to go back to our diagram of where we remove the n, we can now see that basically it's converging, but notice that here, the value of which it converges to, it's not necessarily required that you would know, but notice that it is approaching slowly natural log of 2. So we have that it's approaching natural log of 2, and see like how 0.688 and then 0.6931, etc. It's not really a good estimate necessarily, but if we can make n bigger, then maybe we can lower the remainder that is for this one. So we can see that this, in fact, is converging to the value of natural log of 2, and that the sequence of terms are going from positive to negative, but they're approaching 0 in either case. So what would we say? We would say that this converges basically conditionally. Okay, now if, for example, we had a series such as like the series of negative 1 to the n, and this is divided by n factorial, and this is n equals 1 to infinity. Well, notice that in this case, that if you have, for example, a for this one, actually, like if we look at this one, you would probably need to show that this series has that the nth term will have to be 0. But I don't know if that's enough, though, to show that. So this series is definitely alternating, but if you check it under the absolutes, I'm not sure that that would be enough, because then you might need to do like a ratio test. So for this one, I would say at the moment, like if you were going to try to show for this one, apply the alternating series test. Meaning that if you apply the alternating series test, then in that case, that would probably mean that that it doesn't necessarily converge under the absolutes, right? Okay. But let me look at a different one, actually, that is not so involved, per se. So we'll go ahead and look at the series of negative 1 to the n, and this is going to be divided by the square root of n, and this is going to be n equals 1 to infinity. Okay, so let me just actually go ahead and say apply the ratio test, because I think that will be a little bit better. Okay, but here we're going to go ahead and say, well, if we look at the absolutes, what are you looking at? You're looking at the 1 over the square root of n. But notice this. This is a diverging since you have that the p series says that it's equal to 1/2, which is less than 1. So that means that you would have to basically find a series test to use, of which that would be the alternating series. So you have an equals to 1 over the square root of n, which 1 over the square root of n, we'll do it like this, the limit as n approaches infinity of, let me just fix that, 1 over the square root of n. This approaches 0. Now, in any case, I know that the square root of n is definitely less than or equal to the square root of n plus 1. But if you rearrange that, that's 1 over the square root of n plus 1, less than or equal to 1 over the square root of n, which in fact, this checks out. So we have that this series, it converges. Now note that it converges conditionally by the alternating series test, right? So we have that definitely would converge conditionally, if you will. Now, basically, one thing I suppose that you could do is to look at like what would happen if you rearrange the terms, that is. So like if you were to supposedly rearrange the terms of a conditionally convergent sequence, like what could that happen, for example? And I guess you could probably look at a particular example, and that example could be like if you have the series of -1 to the n plus 1 divided by n, and you know that n equals 1 to infinity, and for example that this is going to be, well, we said 1 over 1 minus 1 over 2 plus 1/3, and then minus 1/4. But we said that it converges to natural log of 2. But let's say that, for example, that you group all of the terms together, for example. So here, what if I was to say, well, parentheses 1 minus a half plus. Now, in this case, what if I was going to say, let's see, what does that look like in any case? So, yeah, so we know that we're going to expand this, and this is what it's going to look like, right? But let's say that we take the half, we group it together, but let's say that we switch out the 1/4, okay? So we switch out the 1/4, so let's put a minus sign right there. Okay, why not? So minus 1/4, okay? But then plus, okay, what comes next is that I still have that 1/3. So I'm going to take 1/3 and I'm going to subtract basically 1/6 plus, well, minus an eighth. And then we'll do plus 1/5 minus 1/10. And, well, okay, so what's going to happen is that, if we repeat this pattern necessarily of rearranging the terms, you're going to get that 1/2 take away from 1 is 1/2. But you still have the minus 1/4, right? But then here you have basically plus, and what is that? That's plus 1/6 minus 1/8, and then that's going to be plus, let's see, plus 1/10. Okay, so 1/10. And then if you repeat this pattern, that's going to be minus 1/12, and then that's going to be plus 1/14. But look at this. You end up with a half multiplied by 1 minus a half, and then you have plus 1/3 minus 1/4 plus 1/5, and then minus 1/6 plus 1/7, and then that just keeps going on forever. But notice that by definition, that's natural log of 2, which is 1/2 natural log of 2. So we see that by rearranging the terms, you obtain a sum that is actually half the original sum, if you will. Okay. Now, in any case, for example, as we move on into working with series and sequences, we will be able to see, how exactly do we have that these sequences, are series, that they converge to a particular value. And one of the most classic ones, for example, if you're part of the math club, then more than likely you've already seen it. But it's basically like how if I look at a particular series, such as like n equals 1 to infinity, and I have negative 1 to the n minus 1, and this is divided by 2n minus 1, basically I can show that this converges to pi over 4, which technically means that if I multiply it by 4, and I go to infinity, this means that this will equal to actually pi. So we have that this equals to pi, but notice that this is a conditionally convergent sequence, actually, a series. Sorry, I keep messing that up. But, if you look at any further ones, like the one that we looked at, like the negative 1 to the n plus 1, that if it's divided by n squared, it goes to pi squared over 12 in either case. So yeah, we'll kind of explore different options in terms of like looking at alternating series and their converging values. But one thing that's kind of interesting is that if you are just needing to show convergence or divergence, then in that case, the values of which that these happen to converge to would not be really relevant, if that makes sense, actually, which is not too bad, but it can be shown nevertheless.